Hey everyone, welcome back to Calculus 1. This will be lecture 18 of the course, and in this we're going to put together a summary of curve sketching and do a few examples using all of the techniques we've learned up until now. Okay, so let's jump into it. So we'll call this 3.6 and we'll call it a summary of curve sketching. Okay. All right. And so having the ability to quickly sketch graphs and curves of functions is extremely important when both learning calculus and when applying calculus. So we're going to look at a bunch of examples, but I want to start with just a few kind of basic guidelines. And of course, these aren't set in stone. It'll depend on the function you're asked to sketch or consider. But frequently, these guidelines will come into play and be extremely useful. So I think kind of the first thing, let's write guidelines here. Sorry, guidelines. There's an E in there. Guidelines. So the first thing really that is important to do that people fail to do a lot of times is to look at the domain and the range of the function. So determine the domain and the range of the function. Right now, usually this can be done just by kind of looking at it, inspecting the thing. Frequently, it's obvious what the domain is and where it's obvious where any restrictions to the domain would exist. And the range is not always as obvious, but usually can be kind of figured out with just some minimum amount of consideration. So I always recommend people do this, specifically the domain being the super important part. The range less so, but still worth looking at, especially if it's easy to see. Okay, the next bit in there would be to identify asymptotes and symmetry of the graph. Okay, so determine any asymptotes. Okay, and we know how to do that using, critical values, specifically domain restrictions, that kind of stuff. Also look, and kind of as part of this, look for symmetry of the graph as well as intercepts. Determine any asymptotes, look for symmetry, and identify any asymptotes, or identify any intercepts, sorry. Now, certainly the y-intercept can be found very quickly, and I recommend always doing that. But in a lot of cases, the x-intercepts are things you can find as well, right? And so we'll do some examples. But this is another example where, anything that you can identify easily, you should. Some of these other things like range and x-intercepts, maybe they're harder to figure out, and maybe they're not worth the squeeze. But if they are easy, if it's a quadratic equation that factors, for example, or something you can plug into the quadratic formula, just find them quick. It can help with the drawing. And then the third guideline would be to locate the x values where the derivatives are 0 or do not exist. And this is like the calculus specific piece of it. So locate any x values where f prime of x equals 0 or f double prime of x equals 0 or do not exist. Okay, locate any x values where the first or second derivative are equal to 0 or do not exist. And then we're going to use these points to determine the extrema and also the inflection points. So use these points to determine the relative extrema and or inflection points. Okay. All right. So I know these are very rough guidelines, but basically, take a look at the function, think through what values of x are appropriate to plug into the function, and more to the point, which values are not available for evaluation in the function. That's the domain. If it's easy and obvious what the range is, make a note of it. Okay. Step 2, you're gonna, using kind of the information from above and then also by inspection, determine any asymptotes. Right, asymptotes are going to play into the range, the domain of the function. So those two are connected. Look for symmetry, right? If it's a quadratic equation, you know it's symmetric. And identify any intercepts. The y-intercept can always be gotten easily just by plugging in x equals 0. But then also look for any x-intercepts. For that, of course, you'll have to solve the equation for x, set the equation equal to 0 and solve for x. And sometimes that's easy to do. Sometimes it's not so easy to do. Take it case by case on that one. And then guideline 3 would be really like the calculus piece of it. So you're going to find the first and second derivatives and then use the machinery that we've been developing over the past handful of lectures to kind of inform you regarding relative extrema and inflection points. Okay, so let's do some examples. We'll do 2 examples in this lecture, and we'll kind of go through these steps with each of them. All right, so the first example, we're going to sketch the graph of, and this will be f of x equals 2 times x squared minus 9 divided by x squared minus 4. All right, so looks like a rational function, polynomials on top and bottom. Okay, so let's just run through the guidelines here. So first off, let's think about the domain of the function. The domain here, well, it's a ratio of 2 polynomials. So the top can be any real number, but the bottom, we do have some restriction on the domain, right? So the domain is restricted by x squared minus 4. So specifically, we would say x squared minus 4 equals 0, implies x squared equals 4, implies x equals plus or minus 2. Right, and so the denominator here, x squared minus 4, is 0 when x is 2 or negative 2, and we can't divide by 0, so the domain of the function is all real numbers except for these 2. Okay, so this is an example where you can pretty quickly figure out the domain. So the domain is equal to x in R such that x is not equal to plus or minus 2. We'll write it like that. There's many ways you could write it. We'll just put it like that. Okay, so any real number except for plus or minus 2. Okay, and the range here, I mean, I think it's not obvious what the range would be. Most likely, though, it's all real numbers. So we're not going to worry about the range in this case. It's also not. It's, as I say, the range isn't super important most of the time. In the case of like a trig function that has like a trig function would have, you know, like 2 times sine of x, for example, would have a restricted range, right? It would be -2 to +2. That sort of thing, that's where range comes into play and is important. In the case of like a polynomial or even a rational function, the range is less important. The domain, however, is important. Let's look at the intercepts. The y-intercept, as I said, is really easy to find. Right? We can just plug in 0 here. F of 0 equals 2 times 0 minus 9 over 0 minus 4. And so what do we get? -18 over -4. And so we get, what is it, about 9 halves then, I suppose. Okay, so the y-intercept is 0, 9 halves. Okay, that's going to be the point where this graph crosses the y-axis. What about the x-intercepts? Well, we can basically solve this equation. In the case of a polynomial, it's very likely that it's solvable easily, especially if it's a quadratic like this. So we can set f of x equal to 0, right? So that means 2 times x squared minus 9 over x squared minus 4 equals 0. Right? And then we can solve for x, right? And so we multiply both sides by x squared minus 4, and then divide both sides by 2, and you get to this. Okay, so basically these two pieces they divide out. And so x squared equals 9. So x is equal to plus or minus 3. So you're going to have x-intercepts at -3, 0, and 3, 0. Okay, so again, this is an example where the x-intercepts are easy to find, worth doing. Okay, all right, so that gives us a bunch of information. All right, so we know that it crosses the y-axis here. We know that it crosses the x-axis here and here. Okay, we know that very likely there are asymptotes at x equals plus or minus 2, right? So vertical asymptotes there. Let's take a look at the derivatives now. So now we'll do some of the actual calculus here. So let's calculate f prime of x. So f prime of x would be d dx, and I'm just going to rewrite the function 2x squared minus 9 over x squared minus 4. Okay. Now, in order to calculate this derivative, we're going to have to use the quotient rule, right? So that will be the denominator, x squared minus 4, times the derivative of the numerator, minus the numerator, times the derivative of the denominator. Okay, all divided by that denominator squared. Okay, so that's kind of the setup. Sorry about that, a little messy there. So that's the setup, and so what we can do then is just go through and calculate all the derivatives. And so here you're going to get, and then the derivative of that inside is 2x. So we'll have to simplify this. We'll come back through and do this, but looks like that, and then it's 2x here. Okay, so that's this part over here. And then that denominator is still x squared minus 4 quantity squared. All right. And basically what you're going to want to do is expand this entire setup here and combine all of the terms. And when you do that, you get, so the 2's can come out front. So basically you can do it like, it'll end up looking like this. You'll have the 2x here, and then x squared minus 4 minus x squared plus 9, and I'm kind of just going through that and eyeballing that. I think that's right. Divided by x squared minus 4, quantity squared, and I pulled the 2's out here. So this 2 and that 2 I just brought out front. And then of course you can combine a bunch of stuff here. So the x squareds disappear, right? They drop out, and I think altogether you're going to have 2. Yeah. So altogether I think you're going to get let's see, 10x, and then in the bottom you'll have x squared minus 4 quantity squared. Okay, and then we'll go ahead and push that 2 through, so it's actually 20x. Okay. All right. So then, let's see. So that's the first derivative. Okay, and I'll just square that. That's your first derivative. We're going to need the second derivative, most likely, to identify inflection points, second derivative test. So let's just calculate it quickly. Now, the thing about differentiation is typically, not always, I guess, but very often the derivatives will tend to simplify, right? So this isn't a good example. I guess the denominator here did double, but your numerator got a whole lot simpler. So let's go through and calculate the second derivative. I think in the case of rational functions that is not always the case, that things will get simpler. But let's go through this one. So the second derivative will be the derivative of the first derivative. So it's 20x over x squared minus 4, quantity squared. Okay, and then it's the same exercise, right? The low d high equal minus high d low, right? So it'd be x squared minus 4 quantity squared times, and I'm just going to do it. It'll be the derivative of the top function, of the top polynomial, the derivative of 20x. So it'll be times 20. Minus 20x times the derivative of the bottom function here, which is going to be 2 times x squared minus 4 times, and then the derivative of the inside, which is 2x. Okay, and then the whole thing divided by x squared minus 4. Now it was squared, we got to square that again, so it becomes the 4th power. Okay. All right. And then let's simplify if we can here. So let's pull the 20 out. Okay, pull the 20 out here and here. And we can see an x squared minus 4 term in both of these, so let's factor that out. And when you do that, you're left with x squared minus 4, and then let's see, minus 4x. X squared, sorry, minus 4x squared. Okay, so you get that up top, and then in the bottom, x squared minus 4 to the 4th power. Okay, so I kind of did a bunch of stuff there, sort of like in one step. But if you need to, of course, just pause the video and make sure that all makes sense. Okay, then we can combine a bunch. We can cancel here, right? So that's the reason for doing that, would be to cancel with the denominator. And so again, you're going to have the 20 outside. And then what you have here is x squared minus 4x squared, so that's minus 3x squared, isn't it? And then minus 4, all of that over x squared minus 4 to the 3rd power, like so. And I think we can, yeah, let's clean this up a little bit better. Let's just write it like this, negative 20 and then 3x squared plus 4 over x squared minus 4 cubed. Okay, so there's a good second derivative. Okay. All right, so we've got the first derivative up here. We've got the second derivative down here. So what can we say about these? Well, they have the same restricted domain, which would make sense, right? So let's note a few things. F prime and F double prime do not exist at x equals plus or minus 2. Okay, so that's the case with the first and second derivative. So we would note that these are critical values, right? Because that's where you're going to frequently find asymptotes or extrema, potentially. Okay, and so then what we could do is we could set, let's find the rest of the critical values. Let's set f prime of x equal to 0. And so doing that, we would get 20x over x squared minus 4, quantity squared equals 0. And from that, you know, we can see that the denominator, we can multiply both sides by that and get rid of it. And so 20x equals 0 implies x equals 0 is a critical point. Okay, got a critical point there. We've got these two critical points. Let's take a look while we're kind of on the subject of critical values. Let's see if there's where the critical values are for the second derivative. So f double prime of x equals 0. That's going to imply that negative 20 times 3x squared plus 4 over x squared minus 4 cubed equals 0. And so we can multiply both sides by x squared minus 4 quantity cubed divided by negative 20. And so then you kind of get to the heart of it really quickly. 3x squared plus 4 equals 0. And solving this for x, we would get x squared equals negative 4/3, right? And so that means x is equal to plus or minus the square root of negative 4/3, all right? So basically, there's no real roots. The only roots of this polynomial, or sorry, this quadratic, are going to be imaginary roots. Okay, so no real roots. So basically, we don't really have to worry about it for the case of our graph of the function. All right, so let's summarize kind of what we have here. So we've got a bunch of critical values to look at. So the critical values are what? Well, x equals plus or minus 2, and x equals 0, right? I think that's it. Yes. So we've got 3 critical values. Let's build a table here to work through these. So we'll have everything less than negative 2 over here. And then we'll have negative 2 to 0 here. And then 0 up to 2 here. And then, of course, the rest of the real number line, everything positive above 2 over here. Okay. All right, so this will be a nice way to kind of summarize what's going on here. And so remember, what we want to do here is we're looking for increasing, decreasing regions. We're also looking for relative extrema. We're also looking for any changes in concavity, so like inflection points. Okay, so let's test a point down here. So let's test x equals negative 3, for example. And we plug that into the first derivative, and I just recommend kind of going off to the side of it on a separate piece of paper and plugging in negative 3 into the derivative that we calculated. And when you do that, you'll find you'll get a negative value. So the first derivative is negative in this region. Okay, what about the second derivative? Again, do the same thing, and you'll find that it also is negative. Okay, and so what does this tell us? Well, when the first derivative is negative, that means it's decreasing. And when the second derivative is negative, that means it's concave down, right? Okay, perfect. Do the same thing here. Test x equals negative 1, right in between those. And at the first derivative at negative 1 is also less than 0. The second derivative there is actually greater than 0. And again, just go off to the side, plug these in and test them. And so here we're going to have decreasing, right? The function will be decreasing and concave up, right? The second derivative being positive. Okay. Same thing here. Let's test x equals 1, f prime of 1, f double prime of 1. All right, plug all this information in. In both cases, oh, sorry, I should have written it like this. They're both greater than 0 here. So we've got increasing and concave down. Okay, and then finally over here, let's test x equals 3. The first derivative is positive. The second derivative is negative. So here it's going to be increasing, concave down. Okay, all right, so that's kind of the summary. Now, of course, I sort of tore through this quickly, but this isn't super difficult to do, right? Just it's a matter of evaluating values of x in these derivatives, it's relatively quick, right? And you really just need to determine whether it's positive or negative. It's not even important what the value is for these tests. Okay, so let's try to graph this thing. Let's see what it looks like. Okay, so we know that we have asymptotes here and here, right? So sorry, between, so this would be like your -2, this is 0, and this is +2. So we know we're going to have asymptotes at the 2 and the -2. So let's just put those in right away. Okay, so this would be 1, 2, -1, -2. So I'm going to sketch in these vertical asymptotes here like that. Okay. We know we have a y-intercept at, what was the y-intercept? It was back at 0, what was it, 1 or? Let's see, I wrote it down. Oh, 9/2. 0 and 9/2. Okay, so 1, 2, 3. So 9/2 would be a little more than 2, right? So we'll just put it right about here. Okay, so we know we've got y-intercept there. Okay, so let's see if we can piece together something. So we've got information on this region over here. We've got information on this region here, and then this region off to the side. So over here, let's see. Well, I think actually, oh, you know, we have actually a limit at infinity that I don't think we figured out first. Let's take a look at this. So what happens to this function as x gets large? We need to take a look at that. So the original function, remember, is this. It is 2x² minus 9 over x² minus 4. Right, so we do need to consider the in behavior here. I kind of skipped over that step. So the in behavior. Well, this is a rational function, right? And so the in behavior, we have a really nice theorem that we talked about last time, I believe, maybe the last lecture, where we talked about how the in behavior is determined by the leading leading terms and basically the dimension, or sorry, the degree of the numerator and denominator. So this is basically 2x² minus 18 on the top and x² minus 4 on the bottom. Now that theorem was all about these leading terms, right? And so in the case where the degree of the top and the degree of the bottom are the same, then we said that the limit as x goes to plus or minus infinity is going to of this thing is equal to a over b, where a is the leading coefficient of the numerator and b is the leading coefficient of the denominator. And so in this case, f goes to 2 as x goes to infinity. Okay. Right, so you can see 2 over 1 would be the ratio. And so what that basically means is that we also have an asymptote here. Right, so we have a horizontal asymptote there. And okay, so that information there was kind of missing. So we need that'll tell us kind of what's happening on this side. So over here we see that the function is decreasing and it's concave down, right? And so it's going to be doing something like this. Right? It can't cross that horizontal asymptote, and it's definitely decreasing, and it can't cross this vertical asymptote, so it's kind of stuck there. Similarly, over here in this region, we see that the function is increasing and concave down. So that is going to be basically doing the mirror image, right? So it's going to be going like that. Okay. Now, in the middle, so look at this region first, we've got decreasing and concave up. So that means the function kind of come down to this point, right? And then this region right next to it, it's increasing and concave down, right? And so that means it's going to be doing, sorry, concave up here. My mistake, it's going to be going like this, isn't it? Okay. So the graph looks something like this. This is a complicated graph because of all of the asymptotes, but you've got sort of the graph sort of sandwiched between these vertical and horizontal asymptotes on this side and also on this side, and then right in the middle it comes down to a low point, which happens to be the y-intercept. Okay. All right, so a lot of stuff going on there, a lot of A lot of ins and outs. But hopefully you can see how it is possible to systematically do this. You just want to make sure that you hit all of the points. And really, if you hit most of the points, if you hit, you identify the asymptote, you identify the concavity and whether the function's increasing or decreasing. And don't forget in behavior, in the case where you can figure out the in behavior quickly. If we hadn't had this, it wouldn't be obvious what's going on either side of this thing. But once you have that in behavior and you have a sense for whether there's a horizontal asymptote or whether the function just increases without bound or decreases, etc., whatever the case may be, once you have all that, it's it's reasonably easy to kind of fit the graph in. Now, of course, like the steepness of the curve, the steepness of the increase here is not part of this exercise, right? All we're trying to do is figure out kind of what the graph looks like in each of these regions. We're not trying to get like the perfect steepness or the perfect inflection, etc. We're just trying to get a sense for it. Okay, excellent. Let's do another example. And this time let's plot which one are we going to do next? Let's do the logistic function. So here we're going to plot f of x equals 1 over 1 plus e to the negative x. Okay, it's the logistic function. So what is the domain? Well, it looks to me like, x can be anything, right? I can plug in positive values, negative values. There's no restriction on x, is there? At no point is this denominator going to be equal to, let's see here, at no point is this denominator going to be equal to 0, so we don't have to worry about that. So we're going to say the domain of the function is the real numbers, all of them, okay? We're not going to worry about the range. Are there horizontal asymptotes, or sorry, any vertical asymptotes to be concerned with? No. There's no vertical asymptotes. There's nowhere this denominator will be equal to 0. What about horizontal asymptotes? I'll do that up front so that I don't forget it. So this one, I think we actually talked about this previously, right? I think this was an example in one of the previous sections, but let's go through this. Horizontal asymptotes. So the limit as x approaches infinity of 1 over 1 plus e to the negative x. Okay, and again, kind of breaking this down, you've got the top to worry about. And then the bottom, now what happens at the top? Well, it's 1 for sure. Now what happens down here? Well, this goes to 0, doesn't it, right? These are positive values of x. When you plug positive values of x into e to the negative x, then this is like 1 over some increasing number, so that becomes just 0. And so this is 1 over 1. Okay, so as x grows large, the function goes to 1. What about on the other side? X approaches negative infinity. It's going to be 1 over 1 plus e to the negative x again. And we'll do this again. Okay, now this time, x is approaching negative infinity, so it's heading further out on the left side of the real number line, right? So these are all negative values. So the top stays the same as in the previous case. But here you've got 1 plus what? Well, this is e to the negative x, right? So all of the x's that you're plugging in are negative values. So this would be like 1 plus e to the positive x, whatever x happens to be, really large numbers. So this is actually going to tend to infinity. This is going to grow without bounds. And so this would be 1 over something like infinity, which would be 0. Okay? So the denominator here is growing without bound, and the numerator is fixed at 1. So this thing is going to head to 0. Okay, so that's good. That means we've got our in behavior. We've got horizontal asymptotes at x equals 1 and x equals 0. What about, let's see, can we find, where's the y-intercept? So that's easy. We set 1 over 1 plus e to the negative x equal to, we plug in 0 this time, right? So that's going to be equal to 1 over 1 plus, now what's e to the 0 power? That's just 1, right? So 1 plus 1, so 1/2. Okay, so the y-intercept is at 0, 1/2. X-intercepts, well, this is not going to have any real roots, is it? Actually, this doesn't, this has no roots, right? If you take this guy here, 1 plus e to the negative x, and you set that equal to 0, there's no, no x value is going to make this equal to 0, right? So no roots, we'll put it that way. Okay, and that makes sense, right? Of course, we probably could have seen that here, right? We've got horizontal asymptote at 0 and at 1, so the function is sandwiched between 0 and 1. It never equals 0, right? So naturally, there's no x-intercepts. All right, what about the derivatives? F prime of x. Okay, so that's d dx of 1 over 1 plus e to the negative x. Okay, we're going to use, let's see, we're going to use the quotient rule here. So it'll be 1 plus e to the negative x times, I'll just write it, d dx of 1 minus 1 d dx of 1 plus e to the negative x, all divided by 1 plus e to the negative x squared. Okay, and what do we get there? Well, we up top here, this is 0, right? So this would be 1 plus e to the negative x times 0 minus, and that's just a 1. Now what's this derivative? Well, the derivative of 1 is 0, and the derivative of e to the negative x is negative e to the x. And so this would be like 0 minus e to the negative x. And then it's 1 plus e to the negative x squared. So this is all gone. And up top you just have, let's see, e to the negative x, right? Negative, negative. So you get that right there. Okay. So that's the first derivative. What about the second derivative? Well, it's going to look real. It's going to have the same kind of moves here, right? So d dx of e to the negative x over 1 plus e to the negative x squared. So I'm going to switch pages here. That's going to be, and I'll just expand this nicely so we can see it. So it'll be 1 plus e to the negative x squared times d dx of e to the negative x minus e to the negative x times d dx of 1 plus e to the negative x squared. Okay, and then we got to square the denominator again. So we've got that. All right. Now let's go through and figure out what these derivatives all are. So this one's a little bit messy. We got 1 plus e to the negative x squared. And then this will be, again, negative e to the negative x. Okay, and then over here. Now here we got to use the chain rule, right? So it'll be 2 times 1 plus e to the negative x, right? And then you reduce the power by 1. And then times the derivative of the inside. Again, that derivative is 0 plus negative e to the negative x. So it looks like that. 1 plus e to the negative x to the 4th power on the bottom. Okay. All right, now we got to do a little cleanup here. So I can factor out the negative e to the negative x. Okay, so I can do that. And I can also factor out 1 plus e to the negative x. I'll do that too. Okay. Actually, yeah, let's just clean it up first. Let's not do the factoring yet. So I've got these two here, and then what is over here? Plus 2e to the negative 2x times 1 plus e to the negative x. Okay, right? I think that's right. Yep, divided by 1 plus e to the negative x to the 4th power. All right, and then let's see, we can factor out this guy. Is this squared? This is squared. Sorry, that square term needs to come down. So we can factor one of those out anyways. Actually, we don't even have to factor it. We can just do the cancellation like right here. So you'll have negative e to the negative x, 1 plus e to the negative x, right? The power reduces by 1 since we're going to cancel it out. And then this one we're going to cancel out also, so plus 2e to the negative 2x. And then down below it'll be 1 minus e to the negative x to the 3rd power. Okay. Okay, and I think we can do a little bit of, let's see here. Let's see, what can we do here? Yeah, we'll just leave it like this. Okay, we'll just leave it like this for now. I think there's more simplification that can be done, but I'm just not seeing it right now. But we'll just leave it like this for now. Okay, so then let's look at the derivatives. What about the first derivative? Well, hold on. We need to simplify this. Let's see. This can be written as, so we can take the e to the negative x, negative e to the negative x out. And then, oh, I see. Okay, yeah. Yeah, so then when we do that, we end up with this, actually. Got it. Okay. And then this will be 1 minus e to the negative x, 3rd power still. Okay. So this actually simplifies down. It looks a little better anyway. It's just still not great, but that's good enough for our purposes. I don't know if there's much more that can be done to make it nicer, but okay. All right, so then next, let's take a look at the derivatives and the roots. So if I set the first derivative equal to 0, then that means I'm saying e to the negative x over 1 plus e to the negative x squared equals 0. And so that means e to the negative x is equal to 0. All right, so we can see, we know that has no solutions. Okay. And what about the second derivative? So the second derivative, that's this guy here, right? So negative e to the negative x times e to the negative x minus 1 all over this mess. Right, when we do that, well, the denominator drops out. And so you've got negative e to the negative x times e to the negative x minus 1 equals 0. And so this guy can drop out as well. So e to the negative x minus 1 equals 0. And let's see, so we would have e to the negative x equals 1, right? Just doing that algebra there. And so where does this work? Well, this works at x equals 0, right? X equals 0 will produce 1. So implies x equals 0. Okay, so so the first derivative has no roots. There's no solutions to that equation when we set it equal to 0. But the second derivative does have a root, and that's at x equals 0. So what does that mean when the second derivative has a root, or when you have a solution to the equation f double prime of x equals 0? Well, that means basically that this is going to be an inflection point. Okay, so we're going to have an inflection point at x equals 0. Okay, let's pull all of this information together and summarize. Okay, so we've got 2 points of interest here. Well, actually, we've got 1 point of interest. You've got x equals 0. Okay, now on one side of it is everything smaller than 0. Right, and on the other side of it, obviously, is everything greater than 0. So again, it always just kind of boils down to testing things. Now we also know that this is an inflection point, right? So that's something to keep in mind. This was identified as a root of the second derivative, so that means it's an inflection point. So let's test some values here. X equals -1 is a good one, and then over here we'll test x equals +1. Plugging in the value for the derivatives. So when you plug in -1 into the first derivative, you get a positive value. When you plug in -1 into the first, or when you plug in +1, what do you get over here? You get a positive value as well. So that means the function is increasing on the entire real number line. Okay, that's what those two pieces of information tell you. What about the second derivative? Well, when you plug it into -1 into the second derivative, you get a positive value. But over here, you get a negative value. Okay, right. So f double prime of -1 is less than 0. Okay, so let's take this and consolidate. So this here means that the function is increasing, and this means it's concave up. Okay, so we've got that. Now over here, it's increasing and concave down. And that makes sense, right? Because this is an inflection point. It's the point where the concavity shifts from up to down, right? So naturally, you would expect to see this down. If this said up, that would be problematic, right? This is an inflection point. So let's take a look at this guy. Let's try to graph it. So we've got our x and our y's here. So here we'll just put the scale like this. Okay, and then this function, we have horizontal asymptotes at 0 and at 1, right? So I'm going to actually make it a little bit bigger. So we'll call this 1. Okay, so you got a horizontal asymptote there. The function had a y-intercept. Where was the y-intercept on this? It was at 0, 1/2, right? So right about here. Okay, the function goes through there. Okay, we'll label it 0, 1/2. Okay, and it's increasing on the entire real number line, and also you got to keep in mind that the x-axis here is a horizontal asymptote as well. Right, so basically the function is going to come down like this. It's going to start low. It's going to cross through here, and then the concavity is going to shift, and it's going to hug this this y equals 1. Right, it's gonna get stuck between these two values. Now again, we don't really have we don't know exactly what the curvature is, whether it's very steep and sharp like like something like this, or whether it's more gradual like this, or maybe it's even more gradual. Right, but that's not important, right? That's not important for this exercise. We're really just trying to get a sketch, a reasonable sketch. And so this is the logistic function, very famous function in mathematics. It's used a lot in lots of areas, lots of applied areas. Okay, so that's a summary of curve sketching. We did a few examples. Again, I know this is complex, but this is the kind of material where, look, if you just go and you plot, you work through 4 or 5 examples, maybe 10 examples. I don't know how many you have to do. It depends on the person probably. But you work through a handful of examples, you'll really get a sense for this. You can really get a sense for how to sketch curves, relatively accurate sketches of curves without actually having to plot individual points. Nobody wants to do that, right? It would take a lot of points to figure out that you've got an asymptote here, right, and an asymptote here. So you don't want to do that. What you want to do is use kind of it's almost like the rules and laws of functions as they relate to the derivatives. to their derivatives. So it's worth the effort. And I think it also like just mastering this kind of stuff really gives you a lot of intuition regarding how functions work and how asymptotes work in particular. That's usually kind of mysterious when you're in pre-calculus, but then Calculus 1 is supposed to shed a lot of light on that, and I think it does. So anyways, that's it for this section, for this lecture. And then next time we're going to shift gears and start and talk about optimization problems, and I think that'll probably be the last lecture of the course. Okay, so that takes care of it for now, and we'll see you all next time.